welcome to bridge busting for yet another year. Now, the purpose of this project is to help students develop a basic understanding of structural phenomena by what we call empirical experimentation. In other words, hands-on trial and error. Now, specifically, each student has done some preliminary research and a bit of experimentation that's led to the design and construction of a bridge to the following specifications. The material must be balsa wood and cotton thread only. No glue is allowed. I'll explain why in a moment. Now, the clear span of the bridge between the two benches that we use in the testing must be 75 centimetres from there to there. Now, that's 50% more than it's been in previous years. Quite a significant change to the rules. That's important because we thought it's time to get a few more variables so we can compare things with the past. So it's spanning now 75 centimetres, which is 30 inches for us old folks. And it must carry a load of 3 ordinary house bricks right in the middle. And most importantly, it must break at a load of 5 bricks. In other words, a safety margin of 2. You see, the intention is not only to build something that is strong enough, but also economically, and not stronger than it need be. Makes sense, doesn't it? Within a certain margin of safety, which is 2 extra bricks in this case. Now, sometimes they do go on and load the bricks beyond that if it takes 5, because sometimes they want to find out how many bricks it can actually take. I'll explain why that's useful in a moment. We use the term bridge, by the way, just deliberately to stimulate the imagination, but it's not to be taken too literally, because you see there's no moving load going across it, nor does anything have to pass underneath. Now that's important, so the bricks can actually be hung from the bridge, or put on top, as must have been the case in this particular bridge, or a combination of both. You'll see that the way in which the bridge is actually loaded very severely affects its stability. Because you see, the higher the centre of gravity of the load, the more likely the bridge is to tip over. In other words, we want the load to work for us, not against us. It becomes pretty evident, in fact, in other words, that it's no good making something that is very strong if it tips over first, because it's unstable. The bridge, by the way, must be self-contained. That means you can't use any buttresses or towers at either end, nor can you bird's mouth it over the edge of the supporting tables. You can't nail it to them either. In other words, it must be possible to lay the bridge across the gap without any other means of support, vertical or otherwise. Now, the joints, they must be bound or spliced. They're very important, and we can only use the linen thread. You see, a glued joint would be totally uncontrollable. It would actually subject the members either side of that joint to the most undesirable stresses. Actually, what I call the ski boot syndrome, where your ankle is locked, and we used to see the most awful leg bone breakages before the advent of today's most excellent safety bindings. A glued joint, you see, would be just like that. It would be too strong, and we would end up with testing the glue rather than the geometry of the structure of the bridge. Actually, you can use the odd pin or two to help you start off the splicing. It holds the pieces together while you're doing it, in fact. Their weight, the weight of the pins, that is totally negligible because each bridge is weighed before testing. There's not much left afterwards anyway, because it is then tested to destruction. Each brick, as a matter of fact, weighs about 2,000 grams. So the design load of 3 bricks is 6 kilos, and the breaking load, 2 extra bricks, is 10,000 grams, 10 kilos. Now, each bridge is going to look very different from each other. This is just one particular type, rather interesting. You can see where it broke, by the way, there. So their designs being that different, it's very, very difficult, not really rather fair, to compare one directly to another. So one way we could compare one bridge to another is to obtain sort of a measure of their efficiency. And this we can actually do by dividing the load they carry, that's the weight of the bricks, by the weight of the bridge itself. In other words, we can obtain for each bridge a ratio of the number of times it carries its own weight. You'll actually see the results come up on the screen. The higher the ratio number, the more efficient the bridge is. Now, you can see that it's in a student's interest to make their bridge as light in weight as possible. And this they can do by using as much linen thread as possible and as little balsa wood as possible. Balsa obviously weighs more than linen thread, but there's a penalty to pay. Instability, as you will most definitely see in a moment. You see, there's a lot to learn, and it's a lot of fun too. So, on with the show.